Yeah. Say again. Did I post on the practice? Yeah, I posted on the practice. Probably not. Yeah. Yeah, I'm gonna say no. How did you find the current practice exam? Yeah, good. Comes from a time when all exams were booked and open book for everybody. So technically, that might be slightly harder than the actual exam. Well, let me let's begin here. I'll make a couple announcements before we actually start. So first of all, you'll notice that I released the solutions to the practice exam just a couple hours ago. Be sure to check your work there. But also, at the end of that Canvas announcement, I don't know how carefully people read these things. They should read them very carefully, but in case you didn't, extra office hours. Today, 3 to 4 p.m. in my office. And of course, don't forget, the reason for this is because we have an exam on Thursday, right, in class. Again, if you're not able to be here, of course, that's fine because of the whole situation that we're all in. But you're expected to take the exam at the same time during the class period, just remotely. Okay, so I'll send an announcement about that later today as well. If that turns out to be a problem for anybody, if it's too sick to actually do it, then we can make alternative arrangements. But in general, you're expected to take it at the same time as everybody who actually comes in and takes it in class. Okay, so Thursday 3 in class. Oh, and I'm so proud of myself. I remember to bring your physical quizzes back. So if you want those back at the end of the class, just go here and collect them. Okay. So as I recall, we had just discussed the second derivative test, right? Wherein we identify critical points, right, of which there are two types. Those where the gradient is equal to the zero vector, and the other ones where our function is non-differentiable, right? And then we can use this determinant of a matrix of second partial derivatives to determine whether this is a local minimum, a local maximum, or neither, which we call saddle point. Okay? So let's start with a new example. So let's suppose that f of xy to 4xy minus x to the fourth minus y to the fourth. And then I'll ask you to find all local extrema. Classify them. Okay, so how do we begin? What's the first thing that we can say about this problem? See it here. Yeah. Yeah, and seeing what we can say about x and y. That's a great start. Remember that only accounts for one type of critical point, but definitely something we should do. And in fact, yeah. Yeah, this is just a polynomial. So it's defined everywhere and differentiable everywhere. And I haven't given you any information about the domain of this function. So we can assume that it's all of R2. So in other words, that's all we have to do. Take the gradient and set it equal to the zero vector, right? There are no critical points of the other kind. Because it's a nice function. Okay? So that's worth writing down, right? So note first, there are only critical points where the gradient of f is equal to the zero vector. So then we should go right ahead and compute the gradient and set it equal to the zero vector. So what's the gradient of f? I.e., first of all, what is the partial derivative of f with respect to x? Yeah. Yeah, good. 4y minus 4x cubed. And the partial derivative with respect to y? Yeah, good. Okay, here's our vector equation, which we're trying to solve. Or if you'd like, this is the same as this is an important point, right? A single vector equation results in a system of equations that we would like to solve simultaneously, right? We'll see very shortly what I mean by simultaneously, but the point is that I have to choose x and y so that both of these equations are satisfied at the same time. Okay? Keep that in mind as we continue to calculate. Okay, so in order for this to be 0 and this to be 0, well, 4 is a non-zero number. So really, I just have the variable parts of both of these have to be 0, right? So that is to say, this is the same as y equals x cubed and x equals y cubed. So how do I solve this system of equations? Yeah. Yeah, I have an expression for x in terms of y. I can plug that in to here to get an expression just in terms of y and see what y values are possible. This kind of trips students up a lot in my experience in this course. There's no systematic way of solving a system of arbitrary equations, right? Yeah, so that's something you can always try. Solve one equation for one of the variables and plug it in to another variable, but we will encounter situations when there's more than just two variables, right? So this is where you have to recall all your algebraic tricks and be ingenious and just try your best to find a solution. Of course, for those of you who know linear algebra, there is a systematic way to address linear equations, but arbitrary algebraic equations, there's nothing we can say in general about how to solve them. There's often, if it is solvable, there's many ways to do it. Okay. We're in a pretty nice situation here, right? So let's just proceed here. Again, just keep that in mind as we, over the next couple of weeks, as we do a lot more of these extreme problems. That you'll have to remember some amount of algebra to be okay. Right? So this is the same as if I plug in this expression for x, y cubed, y to the 9th, which is the same as, or I could just say y to the 9th minus y, which is equal to y, times y to the 8th minus 1 is equal to 0. Okay. So now what can I say about y? 0 or plus or minus 1. Good. Right? If y is 0, everything goes to 0. We have y to an even power minus 1. So if we set this factor equal to 0, then we can have y be equal to 1 or negative 1. Because negative 1 to an even power is 1. So all right. Now, what does this tell us about x? Yeah, right. So x can be equal to 0 or plus or minus 1, right? Taking either of these relations and plugging in the possibilities for y, right? So altogether, how many critical points do we have? 3. Okay, so remember our example from last Thursday. We took all the combinations of possible values of x and y. That was because in that example, the two equations that resulted from the gradient each contained only one of the variables. They were independent of each other for satisfying both of these equations. That's not the case here, right? Both equations involve both an x and a y. There are dependencies between the value of y and the value of x. When y equals 0, for example, both these equations dictate that x has to be equal to 0. Likewise, for y equals 1 or negative 1. When y is equal to 1, x must be 1. When y is equal to negative 1, x must be negative 1, right? This equation, negative 1 to the 3rd, of course it has to be negative 1. This is the kind of analysis that you'll be expected to make on your own. You won't be told this. You have to determine, once you determine the possible x and y values, you have to consider which pairs of them combined solve these equations simultaneously. Yeah? Okay. This is, again, historically something that gets confusing for people. So try to internalize that you have to make that decision at some point. Okay. So now that we have our critical points identified, what should we do? Where our task is to now classify them. Yeah, we should find the second derivatives. To what end? What will we use those for? More or less, that's the idea, yeah. Yeah. The Hessian matrix, yeah. We'll calculate the determinant of the Hessian matrix. Yeah, which you're right, tells us something about concavity. Yeah, that's right. That's definitely the spirit of what you want to do. Okay, so let's compute the second derivatives. Right. So okay, so what's fxx? Yeah, good. Right, we're just taking the derivative of the first component of the gradient with respect to x. How about fyy? Yeah. Yep. Okay, and for mixed partial, it's just 4, right? So remember Clairaut's theorem that because the partial derivatives, the second partial derivatives are continuous, mixed partial agrees whether we look at fxy or fyx. You can see that by differentiating this with respect to y, this gives you 4, right? This is the partial derivative with respect to x. We then differentiate with respect to y, we get 4. This is the partial derivative with respect to y. If we differentiate with respect to x, we just get 4. Okay, so this is Clairaut's theorem in action. In any case, we just get 4 for the mixed partial. Okay. So now, what we want to do is come up with a general formula for the determinant of the Hessian matrix, right? Which was, can somebody remind me what this is? Capital D. Right, which we know how to take the determinant of a 2 by 2 matrix, right? This. So we'll plug in each of the expressions that we just computed for these 3 quantities or functions, I should say. So we get negative 12x squared times negative 12y squared. That's 144 x squared y squared minus 4 squared, 16. Okay. Now we're ready to apply the second derivative test, right? We just want to evaluate this Hessian determinant at each of our 3 critical points: 0, 0, 1, 1, negative 1, 1, negative. Okay. So at 0, 0, what do we get? D evaluated at 0, 0 is equal to negative 16, which I think we can all agree is less than 0. What does this tell us? It's a saddle point. Yeah. Good. Hessian determinant is negative, our analysis is done. Right? We know it's a saddle. Okay, let's continue. At the point 1, 1, the Hessian determinant evaluated there is equal to 144 minus 16, which without actually doing arithmetic, I can tell is positive. Tells us what? Yeah. Yeah, good. So we're not done here. We have to take an additional step and look at the sign of fxx or fyy, either one. It doesn't matter. Okay. And fxx evaluated at 1, 1 is negative 12 minus 1 squared, so negative 12, less than 0. It implies 1, 1 is a local max. Somebody remind me why I can conclude that it's a local max because fxx is. Yeah. Yeah, that is a fact. You're right. But how is it that I can conclude it's a local max by analyzing the sign of fxx at that point? What does that tell me? Sign of fxx. Yeah.
With the sign would be
Yeah, exactly. Right. So the concavity of fxx, I'm sorry, the sign of fxx indicates the concavity of the curve that we get when we slice in the x direction, right? So if we change in the x direction, we're concave down. And because, as you were saying, because the determinant is positive, we know the sign of fxx and fyy are the same, meaning that we have a three-dimensional concavity down, meaning that we're at a local max. Okay, good. So what happens at -1, -1? We evaluate that -1, -1. Again, is just the same as before. And we have to check one of the non-mixed partial derivatives at this point. -12 times -1 squared, -12, less than 0. So again, we have a local max at -1, -1. Okay. Good. So, I'm going to ask you to do a little bit of side reading. This is not going to be on the exam, but I want you to read a couple pages of the textbook. I think it's really helpful to there's some really good pictures that help you visualize what's going on in terms of local max and mins relating to level steps. Okay, so I'm going to ask you to read pages 300 to 302 of the textbook. It's because they have a bunch of really nice visualizations to help you see what's going on. That's what it is related to something that you spent a considerable amount of time studying already, little sense. Okay. One other thing I want to note is So in calculus 1, we have this notion of a second derivative test, right? When the concavity, or sorry, we can evaluate local extreme behavior based on the sign of concavity, right? Whether we're concave down or concave. How else might we tell if something is a local max or min in single variable calculus? There's another common method to do this. Anybody remember what else we might do? Not the second derivative test? The first derivative test. What does the first derivative test say? Yeah. Yeah. So a critical point, if you analyze the change in slope around a critical point, you can tell whether you're a max, a min, or neither, right? So there's an analog of this. There's an analog of this in multivariable calculus, but the problem is that in single variable calculus, there's only two directions of approach to a point that could potentially be a maximum or minimum, right? Come from the left and come from the right. In multivariable calculus, more than two variables or more, you have infinitely many directions that you can approach from. So there is an analog, but it becomes quite a bit more complicated as to what to do. However, remember this whole business of degenerate critical points, where the Hessian determinant is 0. We have no information in that case. These are cases where you have to use this analog of the first derivative test to determine local extrema. So the reason I'm saying all this is because on the next quiz, there will be a guided exercise that will teach you about how to apply the first derivative test. We're not going to talk about it in class beyond what I just said. Okay? So just keep that in mind. If you wanted to do some reading after the exam, I guarantee that will be something I ask you on the next quiz. Okay? All right. So let us reflect back once more on our previous experience in calculus 1. After you learn how to identify local maxes and mins in calculus 1, what's the next part of it? What is the primary application of identifying maximum and minimum values of a function? Yeah. Go ahead. Optimization. Yeah. So that's what we will address now. We're going to learn how to optimize functions of several variables, which in essence is the same procedure as one. However, it becomes quite a bit more complicated in that the second type of critical point, right, where we're not differentiable. In calculus 1, this is just the endpoints of our domain when it's closed, right? Or where the function is valid. The boundary of an n-dimensional, or sorry, a subset of Rn, the boundary of a subset of Rn in general has infinitely many points. So we have to come up with some clever way of addressing how to check, quote unquote, these infinitely many points on the boundary of an arbitrary dimension region. Okay. And you'll see that what happens is we kind of do a cascade of optimization. We do it for the interior of an n-dimensional thing, and then on the n-1 dimensional boundary, and then on the n-2 dimensional boundary of that boundary, we'll go all the way down to doing a one-dimensional optimization problem, just like in calculus 1. Okay. So that sounds like a lot, but see how it's not so bad. Okay, so let's just start right away with this example. So let's suppose a circular metal plate. Occupies the points in the plane satisfying x squared plus y squared is less than or equal to 1. X and y in meters. Let us also assume that temperature is given by T is equal to 2x squared plus 2y squared minus y in degrees Celsius. Okay, very open-ended here. Determine the hottest and coldest points on the plate. Okay. So before we get into computing anything, let's just take stock of our situation. What can we say about the setup to this problem? I'll give you a hint. This is fundamentally different than any problem that we've addressed so far relating to maxima and minimum. How so? Yeah. Well, first of all, we're only dealing with one equation. This is specifying a subset of the plane. Right? Also, they both only have two variables, x and y. So, what information is this giving us here? Yeah. Yeah. So the metal plate is a unit disk. And it's just a filled-in circle, including the boundary, lying at the origin of radius. Okay, good. What can we say about this subset of the plane that we're specifying? Is a subset of R2. Does it have any special properties that we've discussed previously? Yeah, it's closed. It's definitely closed. Okay, good. Note x squared plus y squared less than or equal to 1 is closed. Right? It includes all its boundary points. And furthermore, what else is it? Closed and another, maybe I'll just add this drawing, which we'll refer back to a couple times during this discussion. Here's the subset of the plane. It's closed, and it includes this boundary. What else is important about it topologically? Right? We only talked about 4 different characteristics of sets topologically: closed, open, connected, bounded, and actually there's 5, and compact. What does it mean to be compact? 2 things, closed and bounded. This is bounded, right? Because I can draw an open set centered at the origin around it. Closed and bounded, which implies compact. Why am I making such a big deal out of this? What's nice about compact sets? When they serve as the domain of a continuous function. Well, now be careful here, right? Because since our domain is closed, we know that T is not differentiable at any points that are on the boundary of the domain, because we can't approach it from all sides without leaving the domain. Okay, there's something that we discussed in some detail earlier in the term about what happens when a continuous function has as its domain a compact set. And this is from, think of the calculus 1 version of this. What happens when a continuous function of a single variable has a closed interval as its domain? Yeah. That's definitely true. Yes, the boundaries is all critical points, which is a great point. That means this is different from any example we've looked at so far. We have infinitely many critical points. All the points on this bounding circle are critical points, right? So we have to think of some way to deal with that. But before we even start to address that, remember the extreme value theorem says that if a continuous function has a compact domain, then it must attain a global maximum and a global minimum. Okay. So since T is continuous, the extreme value theorem tells us that T must attain a global max and a global min. That is to say, it is possible to even answer this question, what the hottest and coldest points are, because T is continuous and we have a compact domain. Okay. In general, you're not guaranteed that you can find the hottest and coldest. And think about this. What would it take for this to be non-compact? Let's say it continued off infinitely in some direction. It could continue to get hotter and hotter and hotter, or colder and colder and colder. So it might not make sense to ask what the hottest and coldest are. But in this situation, it does make sense. Okay. So now what should we do? We should identify the critical points, right? That is because, remember we had a theorem last week that told us if we attain a max or a min, it has to happen at a critical point. So if we want to identify the points where these max and mins are attained, we have to identify the critical points. Right? Okay. So let's do exactly that. How should we start? Well, let me make a suggestion. We know how to find critical points of the type where the gradient is 0, right? This is an algebraic, a mechanical procedure. Let's start that way, just because on some level it seems easier, right? Okay, so two types of critical points. Those where the gradient of t is equal to 0, 0. And secondly, where t is not differentiable. We've already addressed this, but let me remind you, the boundary of the disk. Okay, so 1. What is the gradient of t? Yeah, good. So 4x, comma, 4y minus 1. Set is equal to 0, comma 0. Okay, so now take a look at the situation we're in. Our first component of the gradient involves only the x variable. And our second component of the gradient only involves the y variable. So now we're in the situation where solving these simultaneously means just solving them each independently. Doesn't matter because there's no y in this and there's no x in this, right? So to make the first component equal to 0, I have to have x equal to 0, right? That's the only thing that you can multiply by 4 to get 0. Okay, so 0. And to make the second component 0, I have to have y equal to 1/4, right? Only critical point of type 1. And I should say that this is not standard terminology, type 1 and type 2. I just mean that this is the first one I've listed. Okay. So here's a bit of a subtle thing that you should get in the habit of doing. So this is a point where the gradient of t is equal to 0. We should make sure that this actually is in the interior of the disk, right? And since 0 squared plus 1/4 squared is less than or equal to 1, in the interior. Disk. Okay. So let me just make a comment before we go on. What we're trying to do here is identify the critical points where we need to check if we're a global min or max. So since this is a place where the gradient is 0 on the interior of the disk, we'll put that in the list of points where we'll evaluate t at the end of this problem. Okay. Now, let's move on to points of type 2. Okay, so take x, y, which satisfy x squared plus y squared 1. So what we want to do is somehow take the points which satisfy this equation and use the definition of our function to perform an optimization on a function of a single variable. Again, this is a thing where there's no algorithm. There's no series of steps that you can execute to make sure this comes out right. You just have to try to recognize some similarity or some place you can make a substitution, some way to reduce the number of variables using the equation that defines the boundary and the equation that defines the function. So, guesses. Yeah. Yeah, that's one thing you could do. You could try to solve for one of the variables and plug in. That gets a little hairy here because there's square roots. So we'd have to have a plus and a minus, but it's still something, a good thing to try. Yep. Yeah, that's another thing you can do, right? Because it so happens that we have x squareds and y squareds in here. Here's maybe even a faster way. Okay. So let's note that t 2 times x squared plus y squared minus y. In fact, we have an x squared plus y squared all together here. That's not to say what you propose, both of you propose, can result in valid solution. It's just more computation, right? So now I'll just plug in 1 for this, right? Just by this box equation here, the boundary defining equation. Okay. So this implies that now we can express t as just in terms of a single variable y for points on the boundary, right? That is to say, this isn't an expression for t everywhere in this disk, just on the edge, just on the bounding circle. The function t becomes very simple, a function of a single variable. Okay? And I should be careful here. I should specify the domain in which y can exist for this function. But it must be on the boundary. What can I say about y? The absolute value has to be less than or equal to 1, meaning it has to be between -1 and 1, because right, we're square. Y is inclusive between -1 and 1. Okay, so now we reset. Now we want to optimize this function in this domain, just like back to the top of this one. Okay. And again, there are 2 types of critical points, where the derivative with respect to the only variable here, y, is 0, and the boundary points, -1 and 1. Okay. First, let's take the derivative of this. What do we get? Just -1. When is this equal to 0? Never. Never happens. So no critical points. Type 1. Okay, 2. What's the boundary of the domain of this function? Yeah. Y equals plus or minus 1 are the boundary points. Of the domain. Okay. Great. So now what we have to do is lift this situation back up to the 2 variable setting that we started. Okay. So if y is equal to 1, what must x do if the point's on the boundary? Yeah. And how about if y is equal to -1? Also 0, right? Either of these cases imply that x is equal to 0. So we add the points 0, -1, 0, 1 to the list of points to check for global max and min of T. Okay, so before we go on, just take a second to appreciate what's happening here. In order to achieve the global max or min of T, we have to be a critical point either where the gradient is 0 or where we're a critical point of each component of the boundary, right? We started out with infinitely many critical points where we're non-differentiable, but we've weeded out almost all of those because of how our function behaves as a single variable function on the boundary. It has to be max or min in terms of this function as well at the same time as a max or min of T as a function of 2 variables. Okay. Okay. So now what do? We've gone all the way down. That is to say, we've gone to the point where we performed an optimization problem from calculus 1. That's as far down as we can go. What do we do now? We want to determine the max and the min. Yeah, we should plug the critical points that we found were critical in lower dimensions as well into the function T and see which values are highest and lowest. So we have this one point where the gradient was 0 and on the interior. And we have these 2 points, which were critical points on the function restricted to the boundary. Okay. So now plug in. Okay, so here's a little table. Okay, so 0, comma 1/4. Here, 0 plus 2 times 1/4 squared minus 1/4. What does this give me? Oh, yeah. What does this computation give me? I think I calculated this to be -1. Okay. What happens when we plug in 0, comma 1? 0 plus times 1 squared minus 1 is equal to 1. And 0, -1. 0 plus 2 times -1 squared plus 1 equals 3. Okay. So we conclude global max at 0, -1. That is to say, this point. And global min at 0, comma 4. Volts. Okay. Also note. Both of these are strict. Meaning that no other point attains an equally cold temperature or equally hot temperature as these 2 points. 0, comma -1, 0, comma 1/4, or 0, comma -1. Okay. So this seems like a lot of work, but it's kind of amazing that just by successively going down a dimension and checking all the dimensions, we can reduce this problem of a priori. When we look at this, it's like, how do we deal with infinitely many critical points? Well, just have to check a dimension lower. See if you can do an optimization problem with fewer variables. Okay? This is kind of thematic to how we deal with higher dimensions in general. We try to find the way that we can generalize what we know from lower dimensions to higher. Yeah. Exactly, because I'm considering only points on this boundary. Yeah, right. So this is something that will become vital. You have to come up with some, in general, you'll be given some description of a region, which is very often described in terms of inequalities. And then you want to come up with some equations that describe the boundary so that you can come up with some relation to the function that you're trying to optimize and how it behaves on the piece of the boundary that you're considering. Yeah, good question. Okay. So I want to set up a problem, and then we'll actually make the full computation on Wednesday. See how it shapes out. So let's keep the same function. T of xy from last example. But now consider a plate, a metal plate which occupies the triangle. Given by x greater than or equal to 0, y greater than or equal to 0, and x plus y greater than or equal to, less than or equal to. Okay, so this is to say, not always will your boundary of your region be given by a single equation, right? So the first step in any of these problems in a practical way is to draw the region if you can, which in this case, we're restricting ourselves to R2. Shouldn't be too hard, right? So here's our plane. Okay, so first of all, what are these two inequalities telling me? Yeah, I'll be here, right? Now, how about this third inequality? Yeah. Yeah, how did you deduce that? Yeah. Mhm. Yeah, right. If you subtract x, if you look at the boundary part of this, where x plus y equals 1, just subtract x. That's the slope-intercept form. Yeah, you're right there. Same thing. It's just however you see it, right? Okay, so it's 1. It's 1. Here's the bounding line coming from this, and here's our plate. Yeah. So here's the thing. The boundary is in 3 parts. The left side of the triangle, the bottom side of the triangle, and the slanted side of the triangle. Okay. So what we're going to do is come up with equations for each component of this and look at what the function t restricted to each of these boundary components, how that behaves. And we'll do a single variable optimization on each of those functions. T restricted to L, T restricted to B, and T restricted to S. Okay. But before we do that, let's look for a critical point of type 1, which we already know because we didn't change the function t, right? It's just the same as before. Again, gradient of t equal to the 0 vector implies 0, 1/4 is a critical point. However, remember last time we had to check if 0, 1/4 was interior to the disk, which it was. Where does 0, 1/4 lie in the triangle? Yeah, it's like here, right? However, on boundary. So disregard. Now, we'll see this on Wednesday. It should bear out that we find this point again when we consider the L component of the boundary. So we'll see that on Wednesday. Okay, have a good afternoon, and maybe I'll see some of you in a very short while. Yeah. Yeah, we will go beyond. We'll see that on. Oh yeah, don't forget your quizzes if you want to pick them up. Sorry. But yeah, yours will be needed back. Yeah. So yeah, we'll see some example of exactly what you were just asking on Wednesday. Okay. Oh, yeah. Sure. Yeah. We can right away. I don't have anything. Have a good afternoon.
Thank you.
Mm-hmm.